In an earlier video in this chapter, we saw the example where Amy was going to study, and for the different hours between 1, 2, 3, 4, or 5, or 6 hours, there was a calculation given for the corresponding probabilities. So the likelihood that she would spend exactly 1 hour studying was 0.05. The likelihood that she'd spend 2 hours studying was 0.1. And that probability continued in this way. So for each hour, there was a corresponding probability. Now we know from earlier sections that probability is a number between 0 and 1, where 0 means it's an impossible event, not going to happen, and 1 means it's a certain event. So in terms of likelihood, the closer the probability is to 1, the more likely it is to occur. So if we were to ask the question, of the hours listed, 1, 2, 3, 4, 5, or 6 hours spent studying, which of the hours is most likely to occur? So we would look through the different probabilities, 0.05, 0.1, 0.2, 0.4, 0.1, 0.15. And 0.4 is the largest of the given probabilities. So we would say the most likely single hour amount of time she'd spend studying would be 4. Now, as we were answering that question, there was only 6 possible options, selecting the numbers 1, 2, 3, 4, 5, or 6. However, if we really think about this, whenever we're studying or doing homework, it's not like we always do it in exactly 1 hour increments. We might study for 30 minutes, or an hour and a half, or an hour and 40 minutes. We're not only stuck to these 6 different options. So if a friend asks her how many hours will she study, although we have the corresponding probabilities for these equal hour increments, 1, 2, 3, 4, 5, and 6, our real-world experience tells us that she might study 3.5 hours or 5 hours and 20 minutes. So in order to find the expected value based on these potential outcomes and their probabilities, we would follow the following procedure. You take the corresponding data point, so 1, and then you multiply it by its corresponding probability. So 1 times 0.5, and then you just continue down through the table until you've paired every data item and its probability. 2 and 0.1, 3 and 0.2, and add them all together. 4 and 0.4, 5 and 0.1, 6 and 0.15. And now we just need to carefully multiply and add these together in our calculator, and the result will be the most likely amount of time she would spend studying. So 1 times 0.05 plus 2 times 0.1 plus 3 times 0.2 plus 4 times 0.4 plus 5 times 0.1 plus 6 times 0.15. Adding that all together, we get 3.85. So the most likely amount of time she'd spend studying as an exact measure would be 3.85. And let's look at our table of values and see why that kind of makes sense. We earlier said of the 6 different options, definitely the most likely one to occur was 4 hours because it was 0.4. So since it has a significantly higher probability than the other options, the expected value should be pulled close to 4. Now, if we look at the lower outcomes, we see that none of the lower outcomes were anywhere as close as likely to occur as our 4-hour mark of 0.40, and none of the higher outcomes were as likely to occur either. So let's keep in mind the difference of our two questions. The first question says, of these 6 options, which is more likely to occur? And if I'm only allowed these 6 options, then definitely 4 hours is most likely to occur of them. However, if I expand past just these strict values, 1, 2, 3, 4, 5, 6, we know there's actually infinitely many possible times that you could spend studying. It could be 5 minutes, 7 minutes, 20 minutes, 17 minutes, 1 hour and 30 minutes, a large variety of options. So whenever we consider that variety of options, we would need to calculate the expected value. We're not just reading from the table. We're saying based on each entry and its corresponding probability, we would multiply the entry and its probability, add that to the next entry and its probability, and if we complete that through the whole table, we will end up with the expected value. What is the most likely occurrence in this situation based on all possible values? So 3.85 hours is the expected value of time spent working on Amy's homework. Now, what we just did, pairing the entry item and its probability, multiplying those together and adding each multiplicative pair together to get the expected value, is exactly what's represented here in this table. We've just written it in mathematical notation. So let's try to make sense of it, but keep in mind it is simply just the item multiplied by its probability added to the next item times its probability all the way down the list. So in mathematical notation, this x subscript 1 means the first data entry. So these subscripts are indicating which entry you're looking at. So it's kind of an ordering of it. So x sub 2 is the second data entry. And it continues to x sub 3 all the way down to x sub n. The reason we're using a letter here is we want this formula to work in all circumstances. And if it's going to work in all circumstances, I can't necessarily say what the last data entry is because we want this formula to work for only 3 entries or 10 entries or 20 entries. So in mathematics, whenever we want to leave that open for future application, we just label it with the variable n. So it's saying the nth entry. Now each of these things is paired with the corresponding probability. So the probability the first data entry occurs is the probability p of x sub 1. The probability the second data entry occurs is the probability of x sub 2. And this pattern continues until the probability of the nth entry is p of x sub n. So we have a new notation of expected value. So E, the expected value of the data entries x, is calculated as follows. The expected value can be found by taking data entry, the first one, x sub 1, and multiplying it by its corresponding probability, add that to the second entry, multiplied by its probability, and continue to add the multiplicative pair of the entry and its probability until you get to the last entry and its probability. If we correctly add all those together, we will get the expected value. So in our next example, we are asked to find the expected number of boys for a 2-child family. So this phrase, expected number, makes us think of our new idea of expected value. And for this problem, we've actually been given each step that we need to do to kind of break it down piece by piece. So in the future, if you're asked for expected value, this could be a good pattern to follow. You first should write out the sample space. And remember, the sample space is all possible outcomes. So in a 2-child family, we know the possible outcomes are that you could get a boy born first, followed by another boy. Or you could have a boy first and then a girl. Or a girl born first and then a boy. Or two girls. So there's 4 possible outcomes for a 2-child family based on birth order. And next we're asked to write a probability distribution. Now a probability distribution, that's just saying for the possible outcomes, what are their probabilities? It's asking us to create a table like we saw in our previous example. Now in the previous example, the table was given to us, but here we're asked to create it. So let's see how we'd go about doing that. Now for the probability distribution, we need to go back to what are we looking for? What are we measuring? We are looking for the number of boys in a 2-child family. Now let's look at our sample space. We could end up with 2 boys, right? If we get a boy and then a boy. We could end up with 1 boy, whether we get a boy first and then a girl, or a girl first and then a boy. Or we could end up with the situation where we had 0 boys. So the possible outcomes of number of boys in a 2-child family is 0 boys in the case that you have 2 girls, 1 boy in either case that it's boy-girl or girl-boy, or 2 boys in the case that it's boy-boy. Now for each of these possible outcomes, there is a different probability. Now remember, probability is always the number of ways what you're looking at could occur divided by the total options. And in each of these cases, the total number of outcomes is 4. If you have 2 children, you could end up with any of these 4 options for birth order. So in each case, my denominator, or bottom of the fraction, should be 4. Now let's think. How many outcomes would have us with 0 boys? Just 1. So the probability is 1/4. How many outcomes have 1 boy? Well, that could be the boy-girl or the girl-boy. So there's 2 outcomes with 1 boy. And then finally, how many outcomes have 2 boys? Only 1, the boy-boy outcome. So for each of these outcomes, 0 boys has a likelihood of 1/4, 1 boy has a likelihood of 2/4, 2 boys has a likelihood of 1/4. So we have been able to construct, based on our understanding of the possible outcomes, a probability distribution on the number of boys in a 2-child family. So the final step is we are asked to find the expected value. Now that we've understood what could occur, we've written out the probability distribution, so now we need to find the expected value. Keep in mind the expected value should based on a probability distribution, so we need this kind of table to work with. But once we have this table, all we do is we pair the item times its probability plus the next item times its probability plus the next item times its probability. So our expected value of the number of boys in a 2-child family, so I'm kind of describing what we're looking at, is equal to 0 number of boys, the likelihood of that is 1/4, plus 1 boy, the likelihood of that is 2/4, plus 2 boys, the likelihood of that is 1/4, and we'll add all of those together. So we have 0 times 1/4 plus 1 times 2/4 plus 2 times 1/4. And the expected value is 1 from our calculations. So what that means is in a 2-child family, the most common number of boys would be 1. So let's do a few more problems related to expected value. So Mike is a lumber wholesaler, and he is considering the purchase of a railroad carload of very dimensional lumber. He calculates the probabilities of reselling the load for $10,000, for $9,000, and for $8,000 are 0.22, 0.33, and 0.45 respectively. Now, whenever they have a list of these items, so dollars compared to probability, and then they say respectively, that means that the first dollar amount has the probability that's listed first. The second dollar amount has the probability that's listed second. So the list match up in order. So the third dollar amount matches with the third listed probability. Now we're asked, in order to ensure that the expected profit of at least $3,000 from this transaction, how much can Mike pay for the load? So for instance, reselling the load for $10,000 is, of all the options, the least likely, right? 0.22. We know closer to zero, the least likely it is to occur. So the most likely price that he'd be able to sell it for is $8,000. It has a probability of 0.45. And we're asked, in order to ensure a certain profit before he spends this amount of money, how much could he pay for the load in order to make a certain amount in profit? Now, the first thing that we need to do with this problem is remember, what is profit? Profit is not the money that you make from the sale. Profit is the money that you make from the sale, which is the revenue, minus your cost. Because although he might make a certain money selling it, he began with a certain amount of cost, right? So you have to then subtract your initial cost to see how much you have left over. So keep in mind, if you're ever asked about profit in the future, profit is revenue minus cost. Now we have a restriction on profit. Profit needs to be at least $3,000. Now think, what does at least mean? That means we need to be $3,000 or greater. So the least amount of profit we can make is $3,000, but if possible, it'd be good to make more than $3,000. So our profit needs to be greater than or equal to $3,000. But what is profit? It is revenue minus cost. So I could replace this with the equivalent reasoning that revenue, the money we make, minus the cost, needs to be greater than $3,000. Now let's think back about how the question is phrased to try to make sense of what we're looking for. How much can Mike pay for the load of lumber? Based on how that's phrased, do you think that's asking us about the revenue or the cost? So how much can he pay for the load of lumber? That's a description of the cost. So we're asked to find the cost. In the end, our answer should be the cost is some number. So that's what we're looking for. So in working with an equation or inequality, you always try to identify what is the unknown thing I'm looking for. So for us, that will be cost. Let's call it C. And in order to solve the equation, we have to know everything else. So that means I need to find an actual value for the revenue, and I'll substitute that in here, and I'll solve this inequality. Now, there's 3 different revenues listed. $10,000, the likelihood of that is 0.22. $9,000, the likelihood of that is 0.33. And $8,000, the likelihood of that is 0.45. So we have different revenue options. So if we're looking for the most likely revenue, we need to find the expected value of revenue. So in order to find the expected revenue, we know we need our table that relates for the different items, their corresponding probability. So if X is our revenue, and this is our probability of X, we know for a revenue of $10,000, the corresponding probability is 0.22. We were told that at the beginning. For a $9,000 revenue, the probability of that occurring is 0.33. And for an $8,000 revenue, the probability of that occurring is 0.45. So to find the expected value, remember you take the item multiplied by its probability plus the next item times its probability plus the next item times its probability. So let's write that out. And now we just need to calculate this correctly. So we have 10,000 times 0.22 plus 9,000 times 0.33 plus 8,000 times 0.45. And when we calculate that, we get the expected revenue based on the revenue for each different price point and their likelihoods of selling at that price. Our expected revenue is $8,770. So that is the most likely revenue that we would make based on the different prices and their probabilities. So this is the value that we will substitute into our inequality. So we have 8,770 minus the cost needs to be greater than 3,000. So if this is the money we can expect to make, what is our initial cost that we could pay for the lumber in order to ensure that our profit is $3,000 or greater? Now, in solving inequalities, you would solve them in the same way as you would solve an equation, with the only thing that you have to watch out for is if you ever multiply or divide by a negative number, you have to switch the direction of the sign. Now here, I want to get the cost isolated. So I want to get cost by itself, everything else to the other side. So currently cost is being subtracted. Let's add it to both sides. What's done to one side must be done to the other. And we would get 8,770. The sign stays the same direction. 3,000 plus cost. Now to get cost by itself, let's subtract 3,000 from both sides. And we get that the cost paid should be less than or equal to 5,770. So the maximum that he could pay for this truckload of lumber should be $5,770. If he pays less for it, then he can expect a higher profit. But if he pays at most $5,770, he will have an expected profit of $3,000. So in our next example, we are told that a farmer will realize a profit of $150,000 on his wheat crop unless there is rain before harvest. So if there's no rain, the profit would be $150,000. If there is rain before harvest, he will only make a profit of $40,000. So if there is rain, that affects his yield, and then he can only make $40,000 in profit of the wheat crop. So the long-term weather forecast assigns a rain probability of 0.16. So the probability that it will rain is 0.16. Now we know it's either going to rain or not rain, correct? So if it's going to rain, that's 0.16. So the probability of no rain, well, the total probability is 1 minus what we are looking not to happen, 0.16. And that leaves us with the probability of no rain is 0.84. Now, an insurance company will offer crop insurance of $150,000 against the rain for a cost of $20,000. So let's translate what this means. This means that if the farmer pays $20,000 to the insurance company, and it rains, the insurance company will pay $150,000. However, if it doesn't rain, then the farmer will have paid $20,000, and since it didn't rain, the insurance company does not have to pay anything back. So the farmer's thinking through the different situations and wants to calculate from the perspective of expected value. Would my expected profit be better under the idea of insuring or not insuring against the rain? So in this problem, we need to calculate what is the expected profit under two situations. What is the expected profit in the first situation when we insure the crop, and in the second situation when we do not insure the crop. And in both cases, whether we insure or we do not insure, the wheat's profit is dependent on whether it rains or does not rain. And we know in order to find expected values, we need to have our probability distribution table, which says if this occurs, this is the probability. If this occurs, this is the probability. So let's write out our work in an orderly fashion. Let's first begin with what are the expected profits if we insure under the idea of if it rains or if it does not rain. Now we know from above that the likelihood of rain is 0.16. The likelihood of no rain is 0.84. So if we insure, let's figure out the profit in the case that there is rain. And the profit if it does not rain. So we will find the profit and their corresponding probability. We can just write in the probability first. We know the probability of rain is 0.16. We know the probability of not rain is 0.84. So all that's left in this table is to find the profits that correspond to these values. Now let's keep in mind profit is revenue minus cost. So in this case that we've already paid the $20,000 in insurance, that's going to be our cost, because that was paid up front. So in the cost that we already paid, in the case that we already paid $20,000 in insurance, if it rains, the insurance company will pay the $150,000, and we still have a crop to sell. However, since it rained, we could only sell it for $40,000. So we get the payment from the insurance, plus the profit from selling the crop at a reduced price. Now this is the idea of revenue. We have to keep in mind that at the beginning we paid $20,000 for the insurance. So then we subtract out the $20,000 as our cost. So this is revenue minus cost is profit. And that total value, when you add it and subtract in your calculator, is $170,000. And that's related to our probability of 0.16 that it rained. Now, in the case that it does not rain, if it does not rain, then we can sell the crop for $150,000. So that would be our revenue. But we still have the cost that we had to put up front, $20,000 for the insurance. It just happened to be, since it did not rain, the insurance didn't kick in. So we still paid the upfront fee, but since it did not rain, we did not get any payouts from the insurance. However, we were able to sell the crop at the full expected price. So that would be a profit of $130,000. So then the expected profit, if we have insurance, can be found by taking the possible outcomes, multiplying by its probability, plus the next outcome times its probability. So we have 170,000 multiplied by the likelihood of 0.16 plus 130,000 multiplied by the likelihood of 0.84, and we would get an expected profit of 136,400. So the expected profit with insurance is this amount. Now we were asked to compare the expected profit under both options to insure, which we just did, and in the case that we did not insure. So let's now calculate the expected profit if we did not insure. Now in the case that we did not pay for insurance, we still have the two situations. Our profit differs based on if it rains or if it does not rain. So let's make our table. The profit, so we might call this section the not insure. And we'll write down what's our profit if it rains. What is our profit if it does not rain? And based on the information given in the problem, we know the likelihood of rain is as before 0.16. And we know the likelihood of it not raining is 0.84. Now, if you would look back through the problem and think about if we didn't pay insurance, what would be our profit in the case that it rained? What would be our profit in the case that it did not rain? So looking back, they told us that if it rains, the profit would be 40,000. And if it did not rain, it would be 150,000. And since we're not paying for the insurance, and that was the overall profit already given, we can just say the profit if it rains is $40,000. The profit if it does not rain is $150,000. And now to find the expected profit without insurance, we just find the expected value, which says take the item times its probability plus the item times its probability until we go throughout the table. So for us, that's 40,000 times 0.16 plus 150,000 times 0.84. So we'll calculate that. And we would get 132,400 as our result. So that is the expected profit without insurance. Now, if we were just reasoning based off of this calculation, it said, based on the expected profit, should we insure or not insure? We see that the expected profit is higher with insurance. So just from this argument, we would say it would be good to insure the crop. So keep in mind, if you're asked to find the expected value of a certain problem, you need to have the table which lists for each option its corresponding probability. So for us in this problem, it was broken down into the case that if it rains or if it doesn't rain, what are the profits? So we found the profit if it rains if we didn't insure and its corresponding probability, the profit if it does not rain and we didn't insure and its corresponding probability, and then expected value is just adding up those pairs of multiplying the item and its probability.